Okay, now we move on and talk a little bit about derivatives and about how to remove baseline. And I think I'm just gonna go into MATLAB and give some examples. So let me try and generate a little example first. I'm gonna create a peak with some built-in function I have. Here we have a vector. Let me make it a little bit smaller. And I'm gonna make a data set where I have 10 samples. Okay, let me plot the data set. So I just created 10 samples that all have the same shape. Now let me open up the pre-processing window and let's talk a little bit about how we can do derivatives. I'm going to load the data in here and open the pre-processing. Now we don't want to do auto scaling, which is the default, so I'm going to remove that one. But we also have somewhere here, no, that's not what I wanted. Here we have derivatives, and we are using what is called Savitzky-Golay derivatives, and I want to show you how that works. And it's easier to explain here. Let's say we have a curve here, and let's say I want to calculate the first derivative, for example. So in reality, it's not really a curve that we have, it's a number of discrete points. And what I'm going to do is that when I have to calculate the derivative in this point, what I could do would be to take the difference here, and maybe just use the average of those two. But that would be maybe a little bit noisy if I have noisy data. So what we do instead is that we define a window around the point that I want to calculate the derivative in. So let's say I'm taking 3 points on each side. And what I'm going to do now is that I'm going to fit a polynomial to these 7 points. Maybe a second order polynomial like this. Now I have a polynomial, and taking the derivative of a polynomial is kind of easy. So if I want to calculate the first derivative in this point, I simply take the first derivative of this polynomial and I calculate the first derivative of the polynomial in this point, and that's what I put in here. And then I move on to the next window and do the same thing in a window around the particular point here. And I continue doing that all the way till I have calculated the derivative in all the different points. Now, as you can imagine, there's an issue when we get to the end of each vector, because I don't have any points to the left of this. And that might create some artifacts every now and then. We'll see about that in the interface. So, if I want to calculate a derivative, I have to define how many points I want to use. I also have to define the polynomial order, and I have to define whether I want the first derivative, the second derivative, etc. Normally we go for first or second derivative. It's very, very rare that we go for higher order derivatives. We could also say none, and then in essence we would just be doing a smoothing. So if I want to smooth my data, I could do it like this. Let's go for a first derivative. I just want to go back and look at my data. So what's a first derivative gonna look like of these data? Well, it's good to have an intuition about this. Let me show you. We're gonna use the default settings. And what you see is that the derivative of a peak becomes a double peak. And it's worth noting that where we have the peak maximum, the first derivative will actually be 0. So if I have a number of peaks in my data, each of them will essentially turn into a double peak, and that makes the interpretation a little bit more complicated. You have to take that into account when you look at your data. So what about a second derivative then? How would that look? Well, we can do that. Basically, we can do a first derivative again. Now we're doing the derivative of a derivative. And now you see that where we have the peak maximum, where we had it before, peak maximum, we now have a peak minimum. And every peak turns into a triple peak. Let me close this window and this one. Now I don't have to do first derivative twice to do the second derivative. I can also just choose a second derivative here, like this. And that would give me more or less the same. Maybe not exactly the same, but essentially the same. What happens if we make the width very wide? Let's try and do this. And let's see what happens here. Then we run into some strange artifacts, because now the width is basically almost longer than the signal. Well, it's half the signal essentially. And you can see we get some strange artifacts here. So we really don't want to make the width too wide. We want to keep it as small as possible, but enough to not blow up the noise. Let's see. And if you're in doubt how wide to do the window, very often you can just try different ones and see which one will give you a nice result. For example, if you're doing PLS, you can check which one will actually give you the best predictions, for example. Let me close this one, sorry, and let me add some noise to the data. Let's see here. I'm gonna add a little bit of random noise. Gaussian random noise, like this. Let's see how that looks. Oof, that's a lot of noise. Let's do like this. Okay, now let me open the data again. Now the data is much more noisy than it was before. Let's take a look. Pre-processing. And I want to see the effect. Let me do a first derivative again. There we are, like this. If you notice, the derivative actually seems to be more smooth than the original data, and that's exactly because of the window that we're using. If I would make the window much smaller, let's say I do 3, then you see that we run into problems. Now we can sort of see what the spectrum should look like, the derivatized spectrum, but it really is too noisy to see anything. So we need to find the nice compromise where we eliminate the noise more or less, and where we don't run into problems with having too wide a filter. It's typically not super critical. Values between 7 to 15 are often used, depending on how long your spectra are. Another thing you see is that we also run into these end effect at the two ends of the spectra, because we don't have any neighboring points in one of the, at the end. So we can't calculate the filter the way we do throughout the spectrum. And that's a problem that we have to deal with somehow. Well, it's not a big issue. What we can do is that we can eliminate these eventually. There is a setting here saying that we can use this weighted tail to downweigh the edge effects. Let's see what will happen. doesn't change much. In some cases it actually will make a difference, and again you can play around with these and see which one will work better for you. Now imagine that you're also working with data where you have to do some sort of variable selection, and maybe it ends that you will have to exclude, for example, this part of the data. Let me change the color. So let's say you remove this part of the data. Now if you do that and you calculate the derivative and you have a big gap here, then you might run into artifacts here from the fact that you're missing the neighboring points. So what you can do is that you can tell the software to calculate the derivatives using all the points, even though some of them are later on excluded. And if we go back here, that's what this one is about. That's not relevant right here, but it might be if you are doing variable selection, for example. Okay, I'm gonna close this. Let's try and load a data set. I'm just gonna clear my workspace and I'm gonna load this data set. Lots of scattering, we've seen this before, NIR data. Now let me see if a derivative can be useful on these data. Okay, so let's start with doing a first derivative. I'm going to turn this down a little bit. Often when we have spectral data, we could easily have thousands of variables. In this case though, we only have 100, so I'm going to make the filter a little bit shorter. It looks interesting. It looks like we have less signal from, artifacts from the scattering, but it's not really a very nice pre-processing. Let's try and do a second order derivative. It's not as working as well as it was before, where we did the scatter correction and different types of normalization. But we do minimize at least a little bit the scattering. So maybe in combinations with other types of pre-processing, it might be useful. And in any case, it's one of the default methods used for this type of data, also for removing scatter. It's also used quite often when you have a baseline in your data, because if you have a baseline, let's say that you have a baseline, let me just delete this one. Let's say you have a baseline like this and like this. If I take the first derivative of these two spectra, that will eliminate the differences in offset and make them both look like this. So if I'm not interested in the difference that arises from the different offsets, I can actually eliminate those using derivatives. Let's see if we can find an example of that. I'm gonna take another data set. I'm gonna use one of the demo data sets which you find here. If you don't have this shown in your PLS toolbox, you can find it here. Let me just hide it now and say view the cache, typically by date, and it includes also the demo data. And what I want is Raman data. Let me see, I think it's this one. Let me just see. Let's try and load it. I'm just gonna double click on this one. And I wanna plot. Let's see. Yep. So this is Raman spectra. And the thing here is that we're not really interested in the fluorescence, this smooth sort of baseline that we have in some of these spectra. We're interested in the peaks here. That's the stuff that carries information. Let's try and see if we can use derivatives to get rid of those baselines. So I'm gonna go back in the pre-processing interface, and we're gonna choose, oops, no, that's not what I want. That is not useful. I want a derivative. And I don't know, maybe a first derivative is actually enough, because locally this baseline is sort of linear. So I'm assuming that a first derivative might do the job. Let's see. Yeah, that's actually pretty impressive. So the first derivative basically eliminates all the baseline and leaves the information about the chemical peaks. And now we can go on and do data analysis. Now imagine that you were doing, for example, PCA on the data without handling this fluorescence. Well, if you do PCA on the data like this, the main variation is gonna be the fluorescence background. It has way more variance than the chemical information. Whereas here, you basically only see the chemical information. So if that's what you're interested in, you're gonna get much clearer results in whatever modeling you're doing. And that means that doing derivatives would be one way of handling scatter. The downside of that is that your peaks become a little bit more complicated, and that might be an issue. Now, sometimes you may intuitively think that mean centering can remove baselines, but that's actually not the case. And I want to show you, if we try and do mean centering here, if I can find it. Here we are. Let me mean center this data set. So I'm actually just going to subtract the average profile. And you can see that after mean centering, this has not been simplified in any way, because mean centering would only work if there was the same baseline in every spectrum or in every profile. When the baseline varies from sample to sample, then mean centering really doesn't do the trick. But we do have some other methods that we can apply if we want to get rid of the baseline. And these are methods that are specifically targeted to removing baseline. And there are many different methods available for that. In the PLS toolbox, we have a few different ones to choose from. The most simple one, you can say, is what is called detrending. And in detrending, we're just going to fit a polynomial to each and every curve here. So for example, fitting a first order polynomial, then we would fit a straight line to the blue one and subtract that, a straight line to the red one, to the green one, etc. And then we would subtract those. Let's see how that would work. So if I choose detrend, now let me go to the settings here, because I don't know exactly what the settings are. Okay, here we see that it's set to a polynomial first order. Now we can see that that's not going to work, for example, for the blue one. For some of the lower signals, maybe it's going to work, but not for the bigger ones, definitely. So I'm guessing that we would need a second order or maybe even a third order polynomial. Well, we can try and we can see what happens. So now it's a second order polynomial, and it's better, even though it's not actually perfect. Let me try a third order polynomial instead. Let's see. That's pretty good actually. It's not perfect. We have some effects down here, but it's not too bad actually. I'm gonna try fourth order polynomial, but I expect that that might not be better. Let's see. Now I run into problems in this area as well as here. So we seem to be overfitting a little bit. Now what we could do instead is that maybe we could fit a polynomial but exclude the areas where we have peaks. That could be a good idea. And that's this method, baseline on specified points. It's going to open a new window, and in this window we can select what regions should be used for calculating the baseline. I think I want to look at all the data instead of just the mean. Okay, so here we see the data. I might want to zoom in a little bit. It's important that we get parts in the beginning and parts where the curvature is, and also some parts at the end. So let me add some data now. I'll make the window small again, and I'll go back to the mean. Okay, so we select this part, and I'm gonna select this part. I'm also gonna select this part. Oops, let me zoom in. Okay, I'm also gonna select this part, and then I also need to have some samples at the end here, like this. Okay, let me take a look at all the data just to make sure that I didn't include any peaks. Seems quite fine here. Oh, I could easily include more here. Maybe I want to do that. Let me see. Yes, definitely. I'm gonna include all of this. Okay. Let me see. Here we are. And seems that I lost something in the beginning. I want that back. So I'm gonna take this part here. Okay, and now I also have to decide what kind of polynomial I want to fit. I can do a first order, which we know is not enough. So I think I'm gonna go for the third order polynomial. That's the one we tried before, and it sort of makes sense that that would be the right one. Now we're basically doing the same as we did before, but we're only using the specified points. And you can see that we are doing an excellent job here. That's actually a very nice baselining. Now, this is a good way to do baseline estimation if you have well-defined areas without peaks. But sometimes, for example, in chromatographic data, some samples would have peaks all over the place. And then this becomes almost impossible because you can't find regions where there are no peaks in any of the samples, even though you may still have nice baseline in all the different samples. They just appear in different regions. Well, there are some other methods that we can use instead of just fitting a polynomial, and specifically there are these two. There's one called automatic weighted least squares, and there's one called a Whittaker filter. And I think I'm just going to show you this one here. What it does is that it tries to fit a baseline to each and every sample individually. So for example, let's say I'm fitting a second order polynomial here, and then it will look and check for positive residuals. So for example, if we have a very positive residual, it's going to say I'm going to disregard this part of the signal, and then it's going to fit the polynomial but without these areas where we had very positive residuals. And it's going to continue doing that until it converges to a certain baseline. And in that sense, you don't have to specify where the peaks are. The algorithm will automatically discover where they are. Now, there's a lot of settings that you can play around with, but for now, we're just gonna use the default settings. And the only thing we're gonna change is the polynomial that we want to fit. I want to fit a third order polynomial, so I'm gonna write 3 here. Your window may look different from mine, because in the toolbox you can define your sort of how advanced you are. There are 3 different levels, and if we press novice, you're gonna see very few settings, and the further you move on, the more settings you can play around with. And anyway, we only need to define the order. So now we don't need to define where we have peaks or anything, we just define the order. And let's see what happens if I press OK. It's gonna calculate, and it does a very nice job. It's not working as well as the baseline at specified points that we did before, but it's still doing a pretty good job at getting rid of the baseline. The main variation now is definitely just the chemical peaks. So with this, we finished talking about baseline and talking about derivatives.